Okay, so our job now is to solve the system mx double prime plus cx prime plus kx equals capital F of t. And what we're going to do is we're going to solve this in a few different scenarios. So the first scenario that we're going to do is we're going to assume no external force. Okay, so we're going to assume no external force. And one thing that also is going to make our lives easier is to mess with this just a little bit. So we're going to have mx double prime plus cx prime plus kx equals 0. So the external force is 0. And then I want to mess around with the constants here just to make this as nice as possible. So the first thing that we're going to do is divide both sides by m. And then this will give us a monic equation, meaning that the leading coefficient is 1. So this tells us that we have x double prime plus c over m x prime plus k over m x equals 0. And then each of these actually have names. So we're going to let k over m be omega squared. So that's an omega, not a w. I can't really draw it, but let me try one more time. So that's an omega squared. And then c over m, we're going to let be 2 times p. Okay, and what this is going to do is this is going to let us look at the equation x double prime plus 2p x prime plus omega naught, omega squared, x equals 0. Okay, so that's going to be the solution that we're going to have to look at. And there's going to be a few cases. So 3 cases to be exact. The first case is when p is going to be greater than omega. And this is what's called overdamped. Okay, overdampened or overdamped. And when p is greater than omega, let's think about what that's going to mean for us. So if p is greater than omega, then we're going to have, let's see, so our equation x double prime plus 2px prime plus 2px prime plus omega naught squared x is going to give us, in all cases, this is what the equation is that we're going to solve. We're going to look at r squared plus 2pr plus omega naught squared equals 0. And if we complete the square, we're going to have r squared plus 2pr plus p squared equals p squared minus omega squared. And so we have to figure out if p is greater than omega, then this quantity will be positive, and therefore we're going to have r plus p quantity squared is equal to p squared minus omega squared. So that tells us that r is going to be negative p plus or minus the square root of p squared minus omega squared. Now, this is true for all cases, but in our case, when p is greater than omega, that forces this quantity under the square root to be positive, and therefore we have real roots, and therefore we're going to have 2 solutions. We're going to have x of t is going to be c1 e to the minus p plus square root of p squared minus omega squared t plus c2 e to the other root minus p minus square root of p squared minus omega squared t. Okay, so those are going to be our solutions in general. Okay, so that's called the overdamped case. If p is less than omega, so case 2, if p is less than omega, this is called the underdamped case. Then what's going to happen is if p is less than omega, is that you're going to end up with, so same equation, same characteristic equation, I mean, you're going to have r is negative p plus or minus this quantity. But if p is less than omega, then p squared is less than omega squared, and then you're going to have imaginary roots. And so we're going to end up with, x of t. So let's just write this all on a single page. So if p is less than omega, this is the underdamped case. And we're going to end up with x of t is e to the negative pt times c1 cosine of this quantity. It's kind of an annoying quantity to write down, but it's okay. P squared minus omega naught. Did I do that right? Yeah, p squared minus omega naught squared t plus c2 sine of p squared t. Okay, hopefully I got everything in there correctly. Okay, but that's what happens when it's underdamped. And the final case, of course, is when if p is equal to omega, in which case this is called critically damped. And in the critically damped case, we're again going to have the same expression, except if p is equal to omega, then that's going to be 0. And we have r equals negative p as our root, and it'll be a multiplicity 2. So that tells us that our solution is going to be xt is c1 e to the minus pt plus c2 t e to the minus pt. And I want you to notice that in all three cases, in the overdamped, the underdamped, and the critically damped case, so notice that if you were to take the limit as t goes to infinity of all of these cases, you're always going to end up with 0, right? So in all cases, it's always going to settle back down to that equilibrium position. Okay, and so that is that's kind of the basic structure for the spring and mass systems.